Hello class. Today we'll be talking about unsupervised learning. So this is the roadmap which we'll be talking in the next few slides. Let's see what's the difference between supervised learning and unsupervised learning. Basically, supervised learning discovers patterns in the data that relate data attributes with a target attribute. These patterns are then utilized to predict the values of target attribute in future data instances. When it comes to unsupervised learning, the data will have no target attributes. And let's talk about clustering in unsupervised learning. Clustering is a technique for finding similarity groups in data, which are called clusters. Clustering is often called as unsupervised learning task and no class values denoting a grouping of the data instances are given, which is the case in unsupervised learning. Due to historical reasons, clustering is often considered synonymous with unsupervised learning. And this is an illustration of clustering. Basically, we can see three data sets here, which are grouped together, which we'll call as clusters in unsupervised learning. And let's see what is clustering for. Let us see some real life examples. Example one, group people of similar sizes together to make small, medium, and large t-shirts, tailor-made for each person to expensive. One size fits all does not fit all. Second example will be in marketing segment customers according to their similarities. They will do targeted marketing. Well, coming to third example, given a collection of text documents, we want to organize them according to their content similarities. This is producing some kind of topic hierarchy. In fact, clustering is one of the most utilized data mining technique. It has a long history and used in almost every field. Example, medicine, psychology. Let's see what are the aspects of clustering. A clustering algorithm will have partitional clustering as well as hierarchical clustering. A distant function and clustering quality will be intercluster distance, which is maximized quality, and intra-cluster distance is minimized quality. The quality of a clustering result depends on the algorithm, the distance function, and the application.
K-means is a partitional clustering algorithm. The K-means algorithm partitions the given data into K clusters. Each cluster has a cluster center called centroid. K is specified by the user. K-means algorithm works as follows. Randomly choose K data points called as seeds to be the initial centroids. Assign each data point to the closest centroid. Recompute the centroids using the current cluster memberships. If a convergence criterion is not met, go to second step. Stopping or convergence criterion. No or minimum reassignments of data points to be different clusters. No or minimum change of centroids. Or minimum decrease in the sum of squared error. This is an example showing the K-means algorithm. A disk version of K-means. K-means can be implemented with data on disk. In each iteration, it scans the data once. As a centroid can be computed incrementally. It can be used to cluster large data sets that do not fit in main memory. We need to control the number of iterations. In practice, a limit is set to less than 50. Not the best method, as there are other scale-up algorithms. Strengths of K-means: easy to understand and easy to implement, very efficient, and K-means is the most popular clustering algorithm. Note, it terminates at the local optimum if SSC is used. The global optimum is hard to find due to complexity. And coming to the weakness of K-means, the algorithm is only applicable if the mean is defined. For categorical data, K-mode, the centroid is represented by most frequent values. The user needs to specify K. The algorithm is sensitive to outliers. Outliers are data points that are very far away from the other data points. Outliers could be errors in the data recording or some special data points with very different values. Question 2, each cluster has a cluster center called as.
Now coming to the weakness of K-means, problems with outliers, we can see there are two examples here. One is the undesirable clusters and the ideal clusters. An undesirable cluster is where the outlier is very far away, and the ideal cluster is where we know the points are really near to the centroid. Now, weakness of K-means, to deal with outliers, one method is to remove some data points in the clustering process that are made much further away from the centroids than other data points. To be safe, we may want to monitor these possible outliers over a few iterations and then decide to remove them. Another method is to perform random sampling. Since in sampling, we only choose a small subset of the data points, the chance of selecting an outlier is very small. The algorithm is sensitive to the initial seeds. If you use different seeds, we'll get good results. The K-means algorithm is not suitable for describing clusters that are non-ellipsoids or hyperspheres, that is, which are uncomplex shapes. The summary of K-means: despite weakness, K-means is still the most popular algorithm due to the simplicity, efficiency, and easy to understand. Other cluster algorithms have their own list of weaknesses. No clear evidence that any other clustering algorithm performs better in general, although they may be more suitable for some specific types of data applications. Comparing different clustering algorithms is a difficult task. No one knows the correct clusters. Now, coming to the representation of the clusters, it's nothing but how we represent the clusters and how well we analyze the clusters. So some of the common ways to represent the clusters include the most foremost and the simplest way is to compute the centroid and use this centroid to represent each clusters. So, centroid is nothing but in general can be called as a central point between all the points that are mapped on a cluster. So, and one more key property of the centroid is that from the distance from the centroid to each and every node in the cluster will be almost identical. So how do we do this? So first of all, we compute the radius and standard deviation of the cluster to determine its spread in each dimension. So what does this mean? It means that we take an estimate and we assume a number, considering it as a radius, and we compute with that to each and every point to determine a common point which is which is equal in distance to each and every of the point. So that common point can be called as centroid. Now the centroid representation alone works well if the clusters are of hyperspherical shapes. If the clusters are elongated or of other shapes, centroids are not sufficient. So these centroids works with only clusters which are similar to spherical in shapes, because we are using the concept of radius and all to calculate these centroids. So if there are other shapes other than spherical, this centroid method will not be sufficient to calculate. Using classification model, all the data points in the clusters are regarded to have the same class label, example the cluster IDs. Run a supervised learning algorithm on the data to find a classification model. So we can see here we have three different kinds of clusters, namely with ones, twos, and threes. So all the ones are categorized as into cluster one, the twos into cluster two, and threes into cluster threes. Now another representation model is we use frequent values to represent the cluster. This method is mainly used for clustering of categorical data. The example of the categorical data clustering are the K-modes clustering, main method used in text clustering, where a small set of frequent words in each cluster is selected to represent the cluster. Now coming to the clusters of arbitrary shapes and how do we represent them. Hyperelliptical and hyperspherical clusters are usually easy to represent using their centroid together with spreads, that is simply a common center for which is equidistant from all the points in the cluster. Now, the thing that we need to keep in mind is that irregular shaped clusters are hard to represent. They may not be useful in some applications. Using centroids are not suitable in general. K-means clustering may be more useful. Example for making two-size t-shirts. So if the clusters are changing from simpler spherical shapes to complex shapes, a simple centroid will not work for classification. So The final question in our presentation is which shape clusters are hard to represent? The options are A, irregular, B, regular, C, spherical, and D, none of the above. Thank you.